For decades, computation meant massive, rigid machines. It was a time defined by room-sized mainframes crunching physical punch cards, processing logic through strict mechanical rules. Engineers eventually figured out how to shrink those physical switches. Guided by Moore's law, the observation that transistor counts on a single silicon chip double roughly every 2 years, hardware became exponentially smaller and faster. But that shrinking process has hit a physical wall. Transistors are now so microscopic that they brush up against the fabric of subatomic reality, where the predictable rules of classical physics stop working. At this scale, electrons no longer stay where they are put. They engage in quantum tunneling. Quantum tunneling is a subatomic behavior where a particle passes through a physical obstacle it classically shouldn't be able to cross. The electron simply bleeds right through the barrier and materializes on the other side. Subatomic leakage represents the universe asserting its true, probabilistic nature. For years, the hardware industry treated this subatomic behavior as a nuisance. The standard engineering response was to build thicker physical walls to suppress the leaks and force electrons back into predictable paths. Recently, physicists and engineers stopped fighting the machine. Instead of trying to suppress these strange subatomic quirks, they decided to build a new architecture that runs entirely on them. Understanding where computation goes from here requires throwing out the binary logic of ones and zeros to learn a radically different physical vocabulary. A classical bit is an absolute switch. It is restricted to existing as a solid 1 or a hard 0 at any given time, forcing every calculation into a rigid, linear sequence. The new unit of logic is the qubit. A qubit, or quantum bit, operates completely free from those binary restrictions, moving from a flat, two-dimensional switch into a three-dimensional space of possibility. This state is called superposition. Superposition is a quantum property where a particle holds a rich mathematical chord of multiple probabilities simultaneously, as long as it remains unobserved. Because it holds these complex relationships, a quantum system doesn't have to check potential paths one by one. It can explore a massive, exponentially large computational space all at once. Quantum computers solve complex problems using entirely different physical mechanics than classical architecture. Individual qubits communicate through a mechanism called entanglement. Entanglement is a quantum phenomenon where particles become inextricably linked, allowing them to share information instantly without any physical wires connecting them. Albert Einstein intensely disliked this concept. He famously dismissed the phenomenon as spooky action at a distance because the instant correlation defied the known limits of space and time. When you link multiple qubits through this invisible tension, the computational power scales exponentially. Each new entangled particle weaves into a deeply braided web of shared probabilities. This spooky connection has moved out of theoretical physics and into commercial foundries. It is the literal engine that makes quantum parallelism possible. There is a severe vulnerability to this architecture, known as decoherence. Decoherence is the process where a quantum system loses its fragile state due to outside interference, instantly stripping the machine of its computational power. The system is incredibly shy. A single stray vibration, a tiny fluctuation in temperature, or a wandering cosmic ray is enough to shatter the delicate state and turn the calculation into useless noise. The primary engineering challenge involves successfully isolating quantum power from the noise of the classical world. In the everyday world, gathering data is a passive act. You can measure the speed of a car with a radar gun, and the car keeps driving exactly as it was, without being altered by the observation. At the subatomic scale, looking forces a physical change. The Heisenberg uncertainty principle dictates that certain properties of a particle cannot be precisely measured simultaneously, meaning the very act of observation permanently alters the system. This leads to the collapse of the wave function. The collapse of the wave function is the irreversible moment when a forced measurement strips a qubit of its rich probabilities, snapping it back into a rigid 1 or 0. In quantum computing, looking is inherently destructive. If you try to check on the data mid-process, you kill the complex computation you are trying to capture. This creates an operational paradox for quantum engineers. They must choreograph incredibly complex algorithms entirely in the dark, without ever peeking at the process. To get a correct answer, they rely on quantum interference. Quantum interference is a technique where engineers carefully orchestrate the wave functions so that incorrect computational paths quietly cancel each other out, while the correct paths amplify. When the measurement finally happens, it is not to watch the machine work. Engineers force observation explicitly to end the calculation and collapse the system onto the right answer. Humanity has built a machine that abandons classical certainty. We have chosen instead to compute using the exact same probabilistic rules the universe uses to govern itself.